what if I told you that a concept you probably learned in high school algebra was the secret weapon that helped crack one of the most complex codes in all of history? Well, believe it or not, it's true. Let's dig into how some pretty simple math solved a puzzle that seemed completely impossible. Okay, so picture this. It's 1939. World War II is kicking off, and the German military is communicating with a device called the Enigma machine. This thing created a code so complex, so incredibly secure, that everyone thought it was absolutely unbreakable, and that gave them a massive strategic advantage. And you know what? They had every reason to be that confident. The machine scrambled messages with layer after layer of complexity. So for the Allies, intercepting these messages was totally useless. They were just random gibberish. The challenge wasn't just about winning a battle. It was about winning an information war against a code that seemed invincible. To give you an idea of just how tough this was, this number, that's just the number of starting combinations for the 3 main rotors. And that doesn't even count all the other settings on the machine. Trying to just guess the right combination, what we'd call a brute force attack, was completely, utterly impossible. The code breakers, brilliant minds like Alan Turing, they realized they couldn't just throw more computing power at this. That wasn't going to work. They had to outthink it. And the bigger idea they landed on was rooted in a fundamental concept from math, systems of equations. So what is the secret weapon, really? At its heart, it's all about finding a single point of truth where multiple different clues or equations all line up and agree. Let's break down exactly what that means. Think of a system of equations like a puzzle with a bunch of different rules. Each equation is one of the rules you have to follow. So maybe one rule describes the relationship between x and y, and a second rule gives them a totally different relationship. The goal is to find the one, and only one, pair of x and y that follows both rules at the exact same time. And that's what we call the solution. It's like the one magic key, a specific value for x and y that makes every single rule in the puzzle true. If a value works for one equation but not the other, no, that's not it. It has to unlock the entire puzzle all at once. Now here's the thing. Not every puzzle has just one answer. As you can see here, sometimes the rules lead you to one unique solution, and that's where the lines cross. But other times, the rules actually contradict each other, which gives you parallel lines that never ever meet. No solution. And then sometimes, the rules are secretly the same rule in disguise, which means you get infinite solutions all along the same line. So how do we find that key? Well, just like a detective trying to crack a case, a mathematician has a few different tools they can use. We're going to look at the 3 main ways to find that one true solution. The first method is definitely the most visual. You basically treat each equation like a path on a map. You draw the line for the first rule, then you draw the line for the second rule, right on top of it. The solution? It's just the spot where those 2 paths cross. It's the one location that's on both paths at the same time. And here it is in action. It's so clear, right? Each of these lines represents a different rule, and you can see with your own eyes that they meet at one single unique point, 3, 4. That intersection, that's our solution. It's the one pair of numbers that makes both of those equations true. Okay, our second method is called substitution, and I like to think of it as sending in an undercover agent. You take a piece of information from one equation, like you figure out that y is really just x plus 1 in disguise, and you sneakily plug that information into the second equation to see what it tells you. So here's how that works. We figured out from the first equation that y is the same thing as x plus 1. So in the second equation, instead of writing y, we just substitute it. We swap it out for x plus 1. And suddenly, the whole equation only has one variable, x, which makes it way easier to solve. That one move untangles the whole problem. And path number 3 is the addition method, or as I like to call it, the direct approach. This is where you cleverly tweak the equations so that when you add them together, one of the variables just completely cancels itself out, leaving you with just one mystery left to solve. It's actually a really slick move. You might multiply one of the equations by, say, -1. So now you have a positive y in one equation and a negative y in the other. When you add them together, poof, the y's are gone. This eliminates one of the mysteries right away and leaves you with a much simpler problem. And what do you know? It leads to the exact same answer, 3, 4.
Now, cracking wartime codes is, well, it's pretty fascinating, but this isn't just some abstract idea from a history book. This way of thinking is actually used all around us, every single day, to solve some very practical problems.
Oh, a lot, actually. Systems of equations are the hidden logic behind huge business decisions, managing supply chains, even just making a personal budget. They help us find that sweet spot, that optimal point where a bunch of different factors balance out perfectly. A classic example is the break-even point in business. Every company has a cost equation, that's how much they spend, and a revenue equation, which is how much they earn. The solution to that system of equations is the magic number, where they finally stop losing money and can start making a profit. Take a look at this skateboard company. Their costs are one line, and their revenue is another. You can see that when they sell 10,000 skateboards, their costs are way higher than their revenue. They're losing a ton of money. The whole game is finding where those two lines finally cross. And there it is. The meeting point is 50,000 skateboards. That is the solution to their business system. If they sell exactly 50,000 units, their costs and revenue are perfectly balanced. Sell one more and they're making money, sell one less and they're still in the red. Here's another fun one. A circus knows that 2,000 people showed up and they brought in $70,000. They also know what they charge for adult and child tickets. This is a perfect system of equations. We've got two rules: the total number of people, so C plus A equals 2,000, and the total amount of money, so 25C plus 50A equals 70,000. And by solving that system, we find the one single answer that makes both of those rules true at the same time. There were exactly 1,200 children and 800 adults. No guesswork needed. The math just gives us a precise, undeniable answer. So from the highest stakes of a world war, all the way down to the daily operations of a circus, this simple mathematical framework brings clarity. It helps us find that single point of truth among all these competing variables. The real takeaway here isn't about memorizing X and Y. It's about a way of thinking. The codebreakers knew they couldn't just guess their way to victory. They had to find the point of intersection between all the little clues they had. This is about realizing that really complex problems are often just a set of simpler rules. And if you can figure out those rules, you can find the solution where they all meet. So the real question is, what puzzle in your world is just waiting to be solved?